Steve, thank you very much for your kind introduction. Good morning, good afternoon, and good evening, everyone. I'm Genta Kawahara from Graduate School of Engineering Science, Osaka University, Japan. It is a great pleasure for me to have a talk in this interesting workshop at the University of Cambridge. I would like to extend my most sincere appreciation to the organizers, especially Professor Rich Carswell, for their kind invitation. In this talk, I would like to discuss turbulent heat transfer in wall-bounded flows, their thermal convection and shear flow. This is my joint work with my colleagues, Dr. Motoki, Dr. Shimizu, my former student, Mr. Kawano, Mr. Tsugawa, and my student, Mr. Men, Mr. Koike, and Mr. Shirai. Momentum and heat transfer in turbulent flows are governed by the Navier-Stokes equation and the energy equation. In my talk, for forced convection, we introduce Buchinescu approximation into buoyancy term, and forced convection, that is shear flow, we drop the buoyancy term to suppose that the temperature is passive scalar. And for forced convection, in energy equation, we add spatially uniform internal heating corresponding to mean pressure gradient in order to have the consistent configuration for stream high velocity and temperature. In order to do so, we see the similar equation for velocity and temperature and boundary condition. As a consequence, as we discuss later, we see the similarity between heat and momentum transfer. But please note that in the energy equation, we don't have any counterpart corresponding to fluctuation pressure. That could be the origin of this similarity between heat and momentum transfer. We also discuss this later. These are shear stress, heat flux, and energy budget in convection and shear flow between horizontal or parallel walls at Z equals 0 and H. In shear stress, we see viscous stress, Reynolds stress, mean pressure gradient, and wall shear stress represented by friction velocity squared. And in heat flux, we see conduction heat flux and turbulent heat flux, and internal heating and wall heat flux represented by U tau and friction temperature, T tau. And energy equation, energy budget is given by the equilibrium between buoyancy power and energy dissipation for thermal convection, and equilibrium between pressure power and energy dissipation for shear flow. And these equations are obtained from the Navier-Stokes equation and energy equation. And the buoyancy power is related to Rayleigh number and Nusselt number through heat flux equation. And the pressure power is related to friction coefficient through shear stress equation. And we see the similar expression for shear stress and heat flux. This is the reason of similarity between heat and momentum transfer. And now I discussed turbulent Rayleigh-B&eacute convection. It is a thermal convection between the horizontal plate heated from below, cooled from above. And the dimensionless parameter of this system is, of course, Rayleigh number. And if we increase the Rayleigh number, we see onset of thermal convection and eventually fully developed turbulent thermal convection. And in turbulent state, we are interested in the Nusselt number. That is a dimensionless wall heat flux normalized with thermal conduction heat flux. As Srini explained yesterday, in turbulent state, we see the scaling law of Nusselt number with Rayleigh number. The exponents is around 1/3 up to very high Rayleigh number. And we also see the scaling of the Reynolds number based on RMS velocity with Rayleigh number, the exponent of around 4/9. This is we call the classical scaling, and this scaling has been widely observed in thermal convection, especially the canonical Rayleigh-B&eacute convection between horizontal plates heated from below and cooled from above. For this classical scaling, of course, we already have the theoretical interpretation. Here, we are going to briefly explain this scaling intuitively for the case of Prandtl around unity. In the near wall region, we see the thermal conduction layer, and we also have the viscous wall layer. In this configuration, we suppose that Prandtl is around unity, so the thickness of the thermal conduction layer and viscous wall layer have the comparable thickness, and in which we see the significance of the effect of thermal diffusivity and kinematic viscosity. So, in the energy equation, in this layer, we expect the balance between the thermal diffusivity, thermal diffusion, and advection. And the same is true of the Navier-Stokes equation or Burzynski equation in the wall normal direction. Viscous terms, advection terms, and in case of wall normal Burzynski equation, we have the buoyancy term. They would be comparable in near wall layer. And here, U prime is the velocity difference across the layer. And we know that in the thermal conduction layer, we have the temperature difference, delta T. And we solve these two equations to have the velocity scale in the near wall layer, this one, and the thickness of the wall layer, this one. And we record relation between delta and Nusselt coming from definition of delta. We see classical scaling. And in the bulk region, we can drop the effect of viscosity and the effect of thermal diffusivity. And in the wall normal Burzynski equation, we see this balance. Here, U is a characteristic velocity scale in the bulk region, and the delta T prime is temperature difference across the bulk. And we see this balance, and in the bulk region, Nusselt number is given by the turbulent heat flux. This one. Then we solve these two equations to have temperature difference here and characteristic velocity in the bulk region. And this velocity scaling gives us a Reynolds number based on RMS velocity, and that is also consistent with the classical scale. This is the intuitive a discussion on the classical scaling. And this classical scaling has been observed widely in thermal convection. On the other hand, there are the rigorous upper bounds for Nusselt number given by Charlie and Professor Konstantin and by Plastin and Rich. And in these bounds, we see the factor Rayleigh to 1/2. And these bounds are much larger than classical scaling or experiments. And these bounds correspond to the so-called ultimate scaling suggested by Spiegel and Kreutzmann at extremely high Rayleigh number. And this scaling implies that all heat flux scales with delta T times buoyancy-induced terminal velocity, and it is independent of thermal diffusivity or kinematic viscosity. And supposing this scaling, we consider the energy budget equation. We have the Taylor's dissipation law or dissipation anomaly. Epsilon is independent of buoyancy, kinematic viscosity. The ultimate scaling, however, has not been observed in canonical Rayleigh-Benner convection. So how about the convection between cooled or heated rough walls? And in this case, we see the ultimate scaling here. However, if we further increase the Rayleigh number, what we see is a return to classical scaling. So I have to say that the ultimate scaling in this configuration is confined to a limited range of Rayleigh number. Yesterday, Srini mentioned the possibility of the ultimate scaling, maybe in wall-less convection or convection radiatively heated from below. We observe ultimate scaling. But in this talk, I consider the possibility of the ultimate scaling in conventional Rayleigh-Benner convection, heated from below and cooled from above between the horizontal walls. Next, we consider the turbulent shear flow in smooth pipe. And in this case, the forced convection, we are interested in heat transfer and momentum transfer. The momentum transfer is represented by friction coefficient. And here, U is a forced flow velocity, such as bulk mean velocity. And it is very well known that CF decreases with increasing Reynolds number. And in the forced convection, we use Stanton number. That is also dimensionless wall heat flux normalized with characteristic temperature difference and forced flow velocity. It is known that the similarity appears between heat and momentum transfer, implying the linear relation between Stanton and CF. Actually, in smooth pipe flow, we see constant Stanton over CF, implying similarity. So how about rough pipe flow, excuse me. In fully rough regime, we can see constant CF, as shown here. And we recall the relation between CF and epsilon. Constant CF implies Taylor's dissipation. How about Stanton number? From the definition of Stanton number, we know that the constant Stanton implies the ultimate scaling in forced convection because delta T and U are independent of thermal diffusivity. Actually, we substitute buoyancy-induced terminal velocity to here. In thermal convection, we have this expression for Stanton, and the ultimate scaling in thermal convection represents Nusselt scaling with Rayleigh to 1/2, so constant Stanton. However, what we see in rough pipe flow is decreasing Stanton number in contrast to constant CF. It is not good in engineering application because the introduction of surface roughness just enhance the friction, but heat flux. Now we know that the classical scaling has been observed in turbulent shear flow and turbulent thermal convection, and the introduction of surface roughness cannot lead to the ultimate scaling. And we also observe that similarity appears between heat and momentum transfer in turbulent shear flows. Then, where are we heading, or where should we head? One direction could be pursuing good dissimilarity, that is, greater Stanton than CF. Even in the consistent configuration for velocity and temperature, if we see this similarity, the question why is scientifically very interesting. At the same time, in the engineering applications, we would like to have more heat flux and less friction drag. Another is the achievement of the ultimate scaling. Of course, we know it's very hard for us to achieve the ultimate scaling. The question is, if achievable, how? We are going to consider these 2 points. The first question, more specifically, is can good dissimilarity appear in turbulent smooth channel flow even for planned around unity? We are now working on this problem. Dissimilarity between heat and momentum transfer in turbulent channel flow. I will show these results. As Robinson stated in his very well-known annual review paper, there is structural difference in wall-bounded shear flow depending on the height. In the buffer layer, we see a number of streamized vortices, and in the logarithmic layer, we see still streamized vortex and span-wise vortex. Robinson called span-wise vortex arches, and the wake region is dominated by a number of arches. And we found the relevance of span-wise vortices with dissimilarity. So in this part, we are going to consider the relevance of this structural difference in the emergence of dissimilarity in channel flow. Now we recall the rigorous integral expression of Stanton number and friction coefficient. And please note that this part we shift wall normal coordinate Now Z asterisk equals minus H and plus H represents the position of the wall. And as a consequence of integration by parts of Navier-Stokes and energy equation, we have this expression for wall heat flux and skin friction stress. And here we see the contribution from turbulence. They are turbulent heat flux times Z asterisk and Reynolds shear stress times Z asterisk. And here, TB and UB are bulk mean temperature and velocity, respectively. Dimensionless forms of these equations give us Stanton number and friction coefficient. Here we see thermal conduction effect and Reynolds, viscous effect and turbulence effect. And we are considering this similarity represented by Stanton minus shear. If it takes positive sign, implying good dissimilarity, more heat flux and less friction. So we consider the difference between the two for the case of Prandtl equals unity. So we just consider the integral here. We have two terms. One is Z asterisk times T times W primes. And the other is D asterisk U prime W prime. And we have the governing equation or evolution equation for them from Navier-Stokes and energy equation. Here, we have decomposed streamwise pressure term, pressure difference into mean pressure gradient fluctuation about this one and this one. And please recall that in our configuration, we introduce spatially uniform internal heating corresponding to mean pressure gradient because we are interested in the emergence of non-trivial dissimilarity appearing from the consistent configuration. So they are consistent. So if we suppose that at some instant, temperature and velocity are consistent. So these terms are also consistent with each other. So they do not lead to dissimilarity. However, we have here a pressure fluctuation term, and this is the origin of dissimilarity. And please see this term. If this term has negative sign, this one will relatively decrease with respect to this one and leading to positive ST minus CF. That is good dissimilarity. So we consider that possibility. So please know that Z asterisk W prime del P del X is positive. We see good dissimilarity. Now we relate this discussion with political structures. As Robinson stated, we have two typical political structures, streamwise vortices and spanwise vortices. In case of streamwise vortices, of course, low pressure core is elongated in the streamwise direction, so we can see a significant streamwise pressure gradient, of course. So we don't see significant dissimilarity. How about spanwise vortices? We know that in shear flows, cyclonic vortices, spanwise vortices are dominant. In lower half of the channel, this cyclonic vortex has a consistent spanwise vorticity, the spanwise vorticity of consistent sign with mean shear vorticity. So cyclonic vortex rotate in this sense, the upstream of this vortex, we see positive double prime and negative streamwise pressure gradient. And downstream of this vortex, we see the negative wall normal velocity and positive streamwise pressure gradient for negative z asterisk. So we now know that around cyclonic spanwise vortex, we see the positive term implying good dissimilarity, and the same is true of the cyclonic vortex in the upper half of the channel, of course. So now we are looking into the vertical structure in turbulent channel flow. These are the visualization of the vortices by using second invariant of velocity gradient tensor. And we see a number of streamwise vortices. However, if we remove near wall vortices from this field, what we see are more or less spanwise vertical structures. And they are cyclonic. And these cyclonic spanwise vortices actually induce a positive contribution in the integral for ST minus CF. For example, here we see cyclonic spanwise vortex around which we see the positive integral. And we see the predominant positive contribution from the spanwise vortices. We could see this similarity. Good dissimilarity. And this is CF and Stanton. And we see the decreasing CF and Stanton. And they are almost consistent at low Reynolds number, we see difference. Actually, if we take the difference between the two, around, low Reynolds number, at low Reynolds number, we see more or less the same Stanton and CF. This is because at low Reynolds number, the channel is occupied by buffer layer in which we see the dominant streamwise vortices, no dissimilarity. However, if we increase the Reynolds number, we have extending logarithmic layer in which we have spanwise vortices. That's why we see the increasing dissimilarity. And eventually, this dissimilarity decreases down to 0 because Stanton and CF decreases with increasing Reynolds number. So in this way, however, relative difference could be constant at the high Rayleigh number. This is because we expect Stanton and CF might exhibit consistent dependence on Reynolds number, so we expect the constant, but it is left for future study. So now I'm going to talk about the second question, that is ultimate heat transfer achievable in thermal convection or shear flow between horizontal or parallel walls? In order to achieve the ultimate scaling, we introduce wall permeability in thermal convection and turbulent channel flow. And then we confirm the ultimate scaling in more realistic configuration. That is the convection between porous walls. Long time ago, Javier and we introduced wall permeability in turbulent channel flow. As a consequence of Kelvin-Helmholtz instability, we see these distinct turbulent structures. They are large-scale spanwise rolls, and these large-scale roll-induced wall normal velocity fluctuation and largely enhance momentum transfer as shown here. So I expect that the same true of heat transfer. So we are introducing wall permeability in convection and turbulent shear flow. The boundary conditions are here. Please imagine the permeable wall consisting of a number of wall normal straws. If we have pressure difference between here and the plenum chamber, we see the wall normal velocity because of the pressure difference. And if the thickness of straw is very small, in other words, Reynolds number is very small, we expect linear relation between wall normal velocity on the wall and pressure fluctuation. And beta is a positive constant representing the wall permeability. And the straws are oriented in the wall normal direction. We still expect no slip conditions, and temperature on the wall is fixed at constant value. And in thermal convection, we set higher temperature in the bottom wall and the consistent temperature in channel flow. Please note that these conditions tell us that there are viscous conduction layers even over permeable wall. And if we support the Hagen-Poiseuille flow in the permeable walls, we have rigorous expression for beta here, and the dimensionless permeable parameter is given for thermal convection and turbulent channel flow. And here U is buoyancy-induced terminal velocity and bulk beam velocity. And from this estimate, we see in usual or typical configuration, as shown here, beta U would be of the order of unity. And we are going to take the value around unity for beta U. So I can say that what I will show later could be implemented in real situation. Now we consider the thermal convection. And in this case, as I mentioned before, temperature is active scalar, and the permeable parameter is set to these values, 0 and 3. And the Prandtl is set to unity. This is the result. At low Reynolds Rayleigh number, we see classical scaling here, and at the higher Rayleigh number, above Rayleigh around 10 to 7, we see ultimate scaling here. And in permeable case, of course, we see classical scaling at the higher Rayleigh number. This slide shows vertical RMS velocity on the permeable wall. And at low Reynolds number, we see the scaling of vertical RMS velocity with a typical velocity in near wall region in classical state, in permeable wall. So at low Reynolds number, the convection is more or less the same as in classical state. But if we increase the Rayleigh number, we see the critical change to ultimate state. And at higher Rayleigh number, at supercritical in ultimate regime, we see the scaling of vertical RMS velocity with buoyancy-induced terminal velocity. So I can say that in ultimate state, we see significant wall normal velocity on the wall. This is the mean temperature in the impermeable wall case and permeable wall case. And the impermeable wall case, we see thermal conduction layer And in the bulk region, we see the vanishing temperature difference across the bulk. However, in permeable wall case, we see very thin thermal conduction layer. And bulk region, we see the outer scaling of the mean temperature profile with H and delta T. And we see a finite temperature difference across the bulk region. This is a full visualization of impermeable case and supercritical permeable case. And in permeable case, we see small scale thermal plume in thermal conduction layer, as shown here. However, in supercritical permeable case, we don't see small scale plume, and what we see in the thermal conduction layer is a large scale thermal plume. And this large scale plume extends from one wall to the other. What is the difference between two cases? The origin is the onset of large scale thermal plume coming from linear instability. This is a linear critical Rayleigh number in thermal conduction layer on permeable wall. In the impermeable case, we see the critical horizontal wavelengths comparable to thermal conduction layer thickness, small plume. However, if we increase the permeable parameter, we see the onset of very large scale thermal convection. This very large scale thermal convection over the permeable wall can extend to the other wall. Now, I'm going to explain the physical interpretation of the ultimate scaling. In the impermeable wall case or subcritical permeable case, as we discussed before, we see classical scaling. However, in the impermeable, in supercritical permeable wall cases, we know the enhancement of wall normal or vertical fluid motion. So now we don't see any big decrease in near wall region. So wall normal velocity has a single velocity scale and a single length scale of its change. And thermal conduction layer is still here, but it's very thin. So we see the finite and comparable to delta T temperature difference across the bulk region. So wall normal or vertical Burzynski equation give us this balance. Of course, we can drop the effect of viscosity because we don't see any big difference in wall normal velocity. And this balance gives us a typical velocity scale is given by buoyancy-induced terminal velocity, and it is independent of kinematic viscosity, of course. So we see Taylor's dissipation law, and Nussdelt number is given by turbulent heat flux, delta TU, and they are also independent of thermal diffusivity. So we have ultimate scaling, and Reynolds number is given in this form from this velocity scaling, and this is also consistent with ultimate scaling of Reynolds number. And next, we consider the turbulent permeable channel flow. In this case, temperature is passive scalar, and we introduce spatially uniform internal heating, as I mentioned before. And the permeability parameter is set to 0, 0.3, 0.5. Impermeable, less permeable, and permeable cases. And the Prandtl is set to unity. This is the result. We see decreasing Stanton and CF in the impermeable wall case and less permeable wall case. This is a classical scaling, and the Stanton and CF are consistent with each other in each case. And in the permeable wall case, this one, at low Reynolds number, we see the classical scaling, but at higher Reynolds number, we see not only constant CF, but also constant Stanton, implying the ultimate state. And if we compare the Stanton and CF in the classical state, as we discussed before, we see the greater Stanton than CF, and the same is true of the ultimate scaling. We see larger Stanton than CF, and the good dissimilarity is around 10%. Now we compare the flow structures at low and high Reynolds number. Low Reynolds number in classical state and high Reynolds number in the ultimate regime. This is wall normal velocity on the permeable wall. At low Reynolds number, we don't see any significant wall normal fluctuation and its organization. But at higher Reynolds number in ultimate regime, we see the large amplitude of fluctuation in wall normal direction, and the fluctuation is organized in the span-wise direction. It is a consequence of the Kelvin-Helmholtz instability, as indicated in our prior work. Actually, at higher Reynolds number in ultimate regime, we see the very strong large-scale span-wise rolls, span-wise averaged velocity fields. And these span-wise vortices significantly enhance heat and momentum transfer. This slide shows near wall velocity and temperature at low Reynolds number and high Reynolds number. At low Reynolds number, velocity and temperature are quiescent in near wall region. However, at higher Reynolds number, even in linear sublayer, we see the significant promotion of turbulence in near wall region. And what is interesting for us is that velocity and temperature exhibits more or less the same behavior, implying similarity between momentum and heat transfer. This is because we do not have flow separation. And flow separation is stemming from large amplitude pressure fluctuation, and pressure fluctuation give us a dissimilarity. But in this case, no separation. That's why we see similarity. Now we interpret the physical mechanism of the emergence of ultimate scaling in channel flow. In our prior work, we identify the origin of large-scale span-wise rolls to the Kelvin-Helmholtz instability in free shear layer type. Then, in free shear layer with thickness delta L and velocity difference delta U, the RMS velocity scale with delta U, and then dissipation exhibit the Taylor's dissipation. And same could be true of our large-scale span-wise rolls. We have velocity difference delta U and length scale H, and this is a loss. So we have RMS velocity of the order of UV, and implying that we have Taylor's dissipation law, constant shear. And there is no separation, no dissimilarity, that is similarity. So isotherm and isovelocity control would be more or less the same. So temperature fluctuation is of the order of bulk mean temperature. Then wall heat flux scale with TBUV, velocity fluctuation scale and temperature fluctuation scale. And they are independent of thermal diffusivity, so we see ultimate scale, constant stamp.
Genta, you've been going for 45 minutes, just so you know.
Thank you. So we are going to discuss the more realistic configuration. And this is the thermal convection between porous walls, as shown here, the heated and cooled porous wall. And in this numerical simulation, we compute the Nusselt number on the porous wall here. And as you see, at the higher Rayleigh number, we have the ultimate scaling, and low Reynolds number, low Rayleigh number, we see classical scale. And in between the two, we see transition from the classical to ultimate scaling. And this range, we see the scaling, Nusselt scaling with Rayleigh. And this is a big difference from the permeable wall for fixed beta U. Fixed beta U. And we have observed the same result in our experiments of thermal convection between porous wall. As you see, the ultimate scaling and the classical scaling in between, we see the scaling, this transition regime. Now I'm going to explain why we see this transition. At lower Rayleigh number in the transition regime, we see vertical structures, but they are in bulk region, not in permeable, but higher Rayleigh number in the ultimate regime. We see a bunch of vertical structures in porous wall associated with very high energy dissipation, local energy dissipation. So at low Reynolds number, we would be free from vortices and dissipation. Maybe at low Reynolds number in transition regime, the flow in porous wall or hole is laminar. If so, we have again Darcy law here. So beta U for fixed geometry, and U is the buoyancy induced terminal velocities increases with increase proportional to Rayleigh to 1/2. So we have ultimate scale, but in this case, if we increase the Rayleigh number, the wall permeability also increases. So prefactor increases with increasing Rayleigh number. Therefore, we have effective exponents greater than 1/2. Actually, we perform DNS of 2D convection between permeable walls for increasing beta U proportional to Rayleigh to 1/2. We see Nusselt scaling with Rayleigh. However, if we further increase Rayleigh number, as I shown before, vertical structures around porous wall. These separated turbulent vortices induce nonlinearity, so pressure loss now scale with velocity squares, not linear relation. And here we suppose that we have the ultimate scaling, So we have buoyancy induced velocity squared. So let us relate this result to permeable case. In permeable case, we have del zero. And the beta is expressed in this way. And by using this case, so pressure loss U squared, and velocity is of course U. So we have U for beta inverse, implying beta U is constant. So this configuration corresponds to permeable wall for fixed beta U. And in this case, we see ultimate scaling. Why not for this higher Reynolds number, higher Rayleigh number in this part? Now I'm going to conclude my talk. In turbulent channel flow at high Reynolds number, we found that cyclonic span-wise vortices can lead to good dissimilarity. And in turbulent convection and shear flow between permeable walls, we found that large-scale thermal or shear structures can lead to the ultimate scaling. And in turbulent convection between realistic porous wall, we observe that even for fixed geometry, we see saturation down to the ultimate scaling at higher Rayleigh number. These results are encouraging for us. So although they are very hard to achieve, we could further pursue dissimilarity and ultimate state in turbulent flows. Thank you very much for your attention.
Thank you, Genta, for a lovely talk. We have time for a few questions. So if you have a question, please raise your hand, or you could type a question into the chat. I think Srini was the first person to put his hand up.
Okay, here I am. Thank you very much, Genta, for the very interesting talk. In the porous case, what is the height you used for computing things like Rayleigh numbers? Presumably, you ignored the porous part because that's really not part of what you think is the dynamics. But in fact, you can see in your pictures that there is some dynamics going on in the porous part itself, although obviously not as vigorously as in the rest of it. So
thank you.
Isn't that something to worry about? But
thank you very much.
Let me finish with one more question tagged on. And that is, do I understand you right, that if somehow we destroy the momentum boundary layer and do almost nothing for the thermal boundary layer, you can get ultimate scaling?
Excuse me. So let us ask the first question. And as I mentioned, we use the Nusselt number here, estimate here, but being independent of the plane, we have the consistent law implying consistently the ultimate scaling. And even on the bottom wall, that is impermeable, and the top wall. And I'm sorry, I don't understand your second question. Could you please repeat that?
Yeah, the second question was, to attain this ultimate scaling, you have to interfere with the boundary layers in some fashion. And it seemed to me from what you have shown that what is more important is the interference with the momentum boundary layer rather than with the thermal boundary layer. Do I understand it right or not? That's the question.
So I think the both should be necessary, because firstly, the Kelvin-Helmholtz type free shear layer instability could give us the vertical structures, and that could give us the Taylor's dissipation law. And if we see the similarity, that implies velocity and temperature behave the similar way. As a consequence of this similarity, we see the constant Stanton. That is the ultimate scaling. So we see the similarity between the two. So we need the both effect on the momentum transfer and heat transfer, I think.
Okay, thank you.
Thank you. Bérangère, you've got your hand up.
Yes, hello, Genta. Thank you very much for the talk. I was puzzled by your similarity law between wall turbulence and heat flow, because the similarity I had in mind rather was with a plain wet flow, in which you inject energy by moving boundaries. Because in the wall turbulence you discuss, you inject energy inside the flow. So in fact, the way I see it, your wall turbulence with porous boundary is more like probably radiatively heated convection in some sense, because you inject energy inside the flow. And in this way, then I think that your results are very similar of the result by the Sackley group.
I see. I don't think so, because please note that this is forced convection. So excuse me. In order to make the discussion clearly, so we have the similar configuration. But if we replace the heating mechanism, for example, the velocity is a Poiseuille type, but the temperature is wet type. Even in such situation, if we see the similar behavior of the isotherm and isovelocity contour, we see the ultimate scale. Okay.
Okay.
So I mean the internal heating in forced convection is not parallel, plays the same role as in the thermal convection.
Okay. Okay. So I have to think about it. It was a naive question.
If we have any question, please get in touch with me.
Yeah. Okay.
Okay, thanks, Bérangère. We have time perhaps for one more question before we have a break. I have a naive question, Genta. So this follows on from Srini's question about messing around with one boundary layer over another. I mean, if you could somehow just mess around with the thermal boundary layer, say by having a strange thermal boundary condition, like having heat flux, like going up and down, would that be enough? Or do you really need to mess to break both boundary layers?
I see. So regarding Srini's question, my answer is not enough. Just for the case rounded around unity,
okay,
we could see the similar behavior. If the Prandtl goes to larger value and smaller value, maybe we could see the different physics. But just for the case of the Prandtl around unity, so the thermal boundary layer and the velocity boundary layer behave the similar way in our strategy.
Okay, I think Srini's got his hand up again, so maybe you want
I see.
Just a follow-up on the same thing. If you actually look at your talk, one of the slides, which I could not number, I could see that your arguments simply did not imply very much for the thermal boundary layer, but it looked like your velocity boundary layer was more or less disrupted entirely. At least that's the sketch you had. That's the reason for my asking the question. And I appreciate the follow-up. Yeah. Okay. Thank you.
Thank you.
Yeah. I'll write to you if I have more questions.
Yeah, please.
Okay. Thank you.
Okay, that's almost perfect timing for the first talk. So thank you, Genta. We have 10 minutes now, 10-minute break. So we'll reconvene at 10 past the hour.
Thank you very much.
Thanks.